Welcome to Charles Babbage, Ada Lovelace, and the Dawn of Computing. This video will introduce you how to use our slide rule and mathematical tables, items which you will encounter during the game. So we'll start with the most complicated one and do the easy one second. We're going to look at the circular slide rule. There's a physical version that can be made by printing out some templates onto hefty cardstock and joining them together. Or you can go to the URL that's shown on this screen to get a computerized version that is a little bit less capable, but at least portable, not printed on paper. So the paper version looks like this. In the back, the big rectangular sheet is the fixed back sheet of the circular slide rule, and it has three scales on it. Our scales are wrapped around, and they have numbers and gradations, sort of like a ruler, all the way around. So we have the A scale, the D scale, and the K scale on the fixed back sheet. Then on the inner sheet, we have the B scale, the C scale, and the CI scale. And that inner dial rotates. So when you manipulate the actual slide rule, physical slide rule, you'll find that that inner part rotates. Also, we have a rotating cursor, which is used to enter, so to speak, numbers that are going to be our input operands for a calculation or to read out the result of that calculation. So in order to use this, there are some basic things that we should talk about. First of all, the beginning of each scale is the digit 1 that's closest to the scale's label. So you may have more than one 1 on a scale, but the one that's by the letter of the scale, that's its name, is the beginning of that scale. And generally, we read from the start position, moving clockwise on the scale. So we'll look at this example and then come back to it later when I actually ask you to do some practice. But to calculate, let's say a product, z equals x times y, what we would do is rotate the cursor until it's over x on the D scale. Then keeping that cursor fixed, we would rotate the inner dial until the 1 on the C scale is under the cursor. And then keeping the inner dial fixed, we'd rotate the cursor until it's over Y on the C scale. And so in that situation, then our result will be the number under the cursor on the D scale. But when I look at that, it's going to be something like this. Here's my D scale right here, this gray one. My cursor line is here. So it's somewhere between 1 and 1.1 on the D scale. But how do I interpret that value, right? How much is each one of these ticks, for instance? Well, in order to figure out what that number means, we have to have a little bit of numeracy. So a tick on the scale means, well, it depends on what it means, to be honest. The first tick clockwise from the 1 on the C scale represents 1.01. But the first tick clockwise from 2 on the B scale is 2.05. So you just have to be able to figure it out what each tick means based on the numbers that are actually on the scale. So let's see what we mean here on the previous slide. If I have 1 is on the D scale here and 1.1, then each of these is a increment between 1 and 1.1, and there's 10 of them or 9 of them. So these are extra points, hundredths. So this would be 1.12 or 1.02, 1.03, 04, 01, 02, 03, 04, 05. There we go. 06, 07, 08, 09, and finally 1.1. Okay, so you just have to be able to figure that out based on the numbers on the scale, how many ticks there are in between the two numbers. And we have to take a little bit of a numeracy detour here. Where does a decimal point go in this? Because all of the numbers that are on the slide rule are between 0 and 10. Clearly, we're going to be working with numbers that are bigger than that or smaller than that. Where do I put the decimal point? Well, it's up to us. As the human operator of the slide rule, we're responsible for determining where the decimal is placed in the operands and the answers. So if we imagine that our answer is halfway between 4 and 5 on the B scale, for instance, well, that could represent 0.45, could represent 4.5, could represent 45, could represent 450, right? What does that mean? So we have to think of our operands and results all being in scientific notation. Like 1200 or 1200 is 1.2 times 10 to the third, and 0.0012 is 1.2 times 10 to the negative third, right? That should be familiar from high school, but we have to have all of our operands, those are the inputs to a calculation, and read our results as if they're in scientific notation. So we'll have to do some conversion of our inputs, and that would look like this. To convert numbers into scientific notation, if the number I'm given is greater than 10, then I'm going to move my decimal point to the left until there's one digit to the left of the decimal point. And count how many times that move happens. That will be the positive exponent for my number in scientific notation. If my number is less than 1, then I go the opposite direction. I move the decimal point to the right until there's one digit to the left of the decimal point. Counting the number of moves, that will be the negative exponent for the number in scientific notation. So let's look at two examples. 6,770. First, I'm going to add the implied decimal point and now start moving it to the left. Move it once, move it twice, move it 3 times, and now I've got one digit left of the decimal point. So 6,770 is 6.77 times 10 to the third. If I have a smaller than 10 or smaller than 1 value, like 0.02478, I'm going to move the decimal point to the right once, twice, and at that point I have one digit to the left of the decimal point. So 0.02478 is 2.478 times 10 to the minus second. Okay, we can use then other facts about multiplying and dividing numbers in scientific notation to help us out when we work with the slide rule. If I'm multiplying values in the scientific notation, I multiply the parts that aren't powers of 10 and add the exponents. Like 2.3 times 10 to the 3 times 5 times 10 to the fourth is going to be the parts that aren't powers of 10, 2.3 times 5 times 10 to the sum of the exponents, 3 and 4, or 11.5 times 10 to the seventh. And if I want to make that into standard scientific notation, I need to move the decimal place one more to the left, increasing the value by 1 to 1.15 times 10 to the eighth. Similarly, with division, I do the same process, except we subtract the exponents. So 2.3 times 10 to the third divided by 5 times 10 to the fourth. Again, I do the operation, the division on the parts that aren't exponents of 10, and I subtract instead of add. So my result will be 0.46 times 10 to the negative 1. And again, to make it into standard scientific notation, move this decimal point 1 to the right, making it 1 smaller, So my ultimate result is 4.6 times 10 to the negative 2. Another thing that we have to consider is the idea of accuracy, especially when we're working with very large numbers that have large exponents or very small numbers that have large negative exponents. The slide rule is not going to give you exact answers. And to be honest, folks, if you're using the physical ones, they're made out of paper and they're held together with scrapbooking supplies, so they're not the most accurate things in the world. The tool provides approximations, not exact values. But with practice and careful work, we can bring the error rate down to probably around 1%. So we can get in the ballpark pretty easily. Okay, so now let's return to multiplication using the circular slide rule. To calculate z equals x times y, we start with rotating the cursor until it's over x on the d scale. So that's my first operand, and again, that needs to be expressed in scientific notation. Then, while keeping the cursor fixed, I rotate the inner dial until the 1 on the C scale is under the cursor. Then I keep the inner dial fixed and rotate the cursor until it's over Y on the C scale. So, my result, again, in scientific notation, and I have to know what the exponents are going to be, the result Z is going to be the number under the cursor on the D scale. Okay, so let's go ahead and calculate a number, and we're going to do a relatively simple one. We'll do 9 times 6, and I'm going to use the online slide rule to show you how this works. All right, now I've got this online version pulled up. It doesn't all fit on my screen, but I can manipulate it with my mouse. So if I use my mouse here, the inner rings with the B, C, and CI scales rotate while the outer ring stays in place. And then if I want to switch to cursor location or rotation, I click my button, the cursor turns red, and I rotate that as I see fit. So we're going to start with our multiplication of 9 times 6. So to multiply two numbers, I would put the cursor until it's over 9 on the D scale. So I'm going to move it to here. There's my 9. Then, while holding the cursor steady, which in this case I'll change it to disk rotation, I'm going to rotate the inner circle until the 1 on the C scale, which is right here, is underneath the cursor. Try to get that as exact as I can. And then I go back to moving the cursor. I move my cursor until it's over the value Y on the C scale. So I'm doing 9 times 6. I want to rotate this till it's over 6 on the C scale. And then if I look at my D scale on the outside, 5.1, 2, 3, 4. So 5.4, and multiplication would be 5.4 times 10 to the 1, right? 54 is my answer. So that's how I would do multiplication with the slide rule. So now it's your turn. I want you to calculate these products. 8 times 7, 2.3 times 4.5, 123 times 360, and 191,622 times 478,128. So if you're watching this on the video, pause the video right now, grab your circular slide rule or the circular slide rule app, and make those calculations. For 8 times 7, we find that our cursor is over the 5.1, 2, 3, 4, 5, 6. And again, knowing where our exponent goes, we find that 8 times 7 is 56, right? And that is the exact answer. Of course, I'm off a little bit because, again, Guys, this is made out of paper and scrapbooking supplies. It's not the most accurate device in the world. But when I looked at that, I would think, yeah, that's 56. Next problem. My second problem, if I look at my scales here, this is between 1 and 1.1 on the D scale. So 1.01, 1.02, 1.03, and a little bit. So let's say 1.032. And since I have, these are both already in scientific notation, my result would be 1.032 times 10 to the first, or 10.32. And again, you just kind of have to know that in this case because these don't have exponents. But if I have something that's a little over 2 times 4.5, it's going to be over 10. Okay, because 2 times 4.5 would be 9. My actual answer then is 10.35, so we're not too bad. For problem 3, here's my D scale. I'm between the 4 and the 5. So 4.1, 2, let's see, did I measure that right? 1, 2, 3. Let's see, 4, 5, 6, 7, 8, 9. No, I'm not counting that right. 9, 8, 7, 6, 5, 4. There we go. I'm looking at this one, not that one. So 4.4 and maybe a little skosh. 4.41 is my answer. And looking at my exponents, 10 to the second, 10 to the second, add those together, it's 10 to the fourth. And so I move this 1, 2, 3, 4 to the right. In other words, pad 2 zeros, 44,100. And my exact answer is 44,280. So again, we're in the ballpark. And on my last problem, now here's the 9. So I'm almost one tick to the right of the 9. And these each represent 0.1. So 9.1, 2, 3, 4, 5, 6, 7, 8, 9, and then back to the 1. So this is going to be 9 or 1.9 something, or 9.09 something. There we go. Not quite to the 1, right? 9.09, here's our answer. My exponent, this was 10 to the 5th, 10 to the 5th, add those two together, 10 to the 10th. And so move this decimal place to the right 10 places, and you end up with this answer, which is 90 billion. And the exact answer is 91,619,000,000. Okay. All right. The other operations that you can perform with the slide rule are explained in the GS1 slide rule instructions document, and that is on your Canvas. Let's finish with calculating the cosine of theta using a mathematical table. This one is much easier. And remember that other functions like trigonometry, logarithms, and so on were calculated and then recorded in mathematical tables. And so whenever I needed to know the answer to one of those questions or those functions, I would look it up in the table. And our basic procedure to look up cosine theta, where theta is an angle in degrees between 0 and 360, is to go down to find the row with the integer part of the angle, and then across that row to find the column closest to the fractional part of theta. That cell will be the table value for cosine of theta. So for example, on the left here, this is a portion of a cosine table. And I suppose I want to calculate the cosine of 22.36 degrees. First is to scan down the rows until I find the row labeled 22. That's the integer part of my angle. So I go down first. And then I go across to find 3.6. Well, I don't have 3.6 columns. I've got 3 and 4. So this will be somewhere in the middle, okay? And in row 22, those are both 0.925. So I will take something halfway between those. In our case, they're the same, so my value will be 0.925. And the calculator value is 0.9248. So within rounding, that is the correct value. See, much easier than the slide rule. All right, here's your assignment now. Again, pause the video, use your table of cosines, which is on Canvas, to find cosine of theta for these angles. And as we go, we should find that the cosine of 25.1 is approximately 0.906. The cosine of 58.4 is about 5 or 0.524. The cosine of 113.7 is about negative 0.402. And the cosine of 186 is approximately negative 0.995. So that gives you a taste of what calculation was like in Babbage's time. People had to rely upon things like the slide rule and mathematical tables to do their calculations. And Babbage was very much interested in mechanizing that process to remove the possibility of human error.